Okay, good evening, uh, everyone. So let's start. So if there is any doubt in the previous section problems, then you can ask. Or if there is any doubt in any of the lecture notes, then also you can ask. Otherwise, we will start by solving some sample problems. I hope my screen is visible to you.
Yes, sir.
Okay. So is there any doubt or anything specific that you want to discuss
Um,
from the
sir,
lecture?
there's a doubt in practice assignment 3.
Practice assignment 3. Okay, that we will probably discuss. We can start first by practice assignment 3 itself. What you say?
Um, okay, sir.
Okay, so in which question you are having doubt?
In the first question.
Oh, first itself. Let me just take that question. So I'm just copy pasting the question from the course website. So it's there, right? This is the first question, right? Determine which of the following cases
Yes,
H
sir.
isomorphic to the group G. So, are you familiar with the group isomorphism? Or when we say two
Um,
groups are isomorphic,
yes, sir. When there's a homomorphism, which is also a bijection.
homomorphism, which is also bijection. Okay. So, uh, so here, in first case, G is the group of integers. Let me just give some numbering to it. So, were you able to solve the first part?
Yes, sir. All except for the second part. I think I know the solutions for all of them except the second one.
So, let us discuss it one by one. So, first part says G is your group of integers under the operation of addition, and H is the real set of real numbers which forms a group under addition. So thus both these groups isomorphic to each other.
No, sir.
Okay, what's the reason?
So R is uncountable and uh, G is countable, so there can't exist a bijection.
Yes, so there can't exist a bijection. So we so definitely they are not going to be isomorphic. So, solution to the first part, as Prerna pointed out, Z is countable and R is uncountable. Therefore, there exists no bijection. Or let me just write it in words only. Therefore, there is no bijection between Z and R. Hence, uh, Z is not isomorphic to. I should not write Z itself. Z has no meaning. So Z plus, that means Z under the plus operation is not isomorphic to R plus. Uh, Now the second part, R is the group of non-zero reals with multiplication, and C star is the group of non-zero complex numbers with multiplication. So are these group isomorphic to each other?
Um, Probably not, but um, I'm not sure as to either how to disprove or prove it.
The cardinality is same, right?
Yes, sir.
Then, so by there should be some bijection.
Yes, sir.
Then can that bijection is also, we can say that is it it is also the group bijection? Means are they isomorphic?
Um, but I couldn't find any homomorphism from it. So or even or even some explicit function which was bijection. So
But that won't be suffice, right? So what properties of homomorphisms you know?
so the identity maps to the identity.
Identity maps to identity, right?
Yes, sir.
Now, what else we can say?
And phi of a star b equals phi of a star phi of
Mhm.
b. If a and b are elements of the group.
Okay. So there can be more than one proof to show that they are not isomorphic, and both use almost every proof uses the fact that phi of one maps to one, because that's the basic information we have about the homomorphism, right? So let's start by first assuming that there is a homomorphism, and then we will come to a contradiction. So the one thing is clear, right? The cardinality part won't give us contradiction, right?
Yes, sir.
So only thing we have to check is the homomorphism part, right? So let's try to do that. So let me first start with this notation. So this notation you know, right? The set of, or simply I will just write R minus 0 and C star is. So this is a very common notation. Any set S star means uh, S minus the set of non-units. Non-units means those which do not have a multiplicative inverse. So here only 0 is the element which don't have a multiplicative inverse. So R star is R minus 0 and C star is C minus 0. So let phi be a homomorphism, or instead of homomorphism, I will assume it's an isomorphism, because there will be a trivial homomorphism. So homomorphism part won't be a problem. Isomorphism we need, right? Because we can simply map everything to identity. So there is a homomorphism. The contradiction will come when we assume it's a isomorphism. So let phi be isomorphism from C star to R star, right? Then what we know, then we know that phi of 1 will be mapped to 1, right? Here, this one is the multiplicative identity of C, and this is multiplicative identity of R. Since in this case, both numbers are same, so we are denoting it by same symbols. Okay. Now, uh, can you tell me what is phi minus 1? This is not very clear.
Minus 1 itself.
Why?
So phi of 1 plus minus 1 should be.
So plus we are not supposed to use,
Oh,
because we are
sorry.
just we can just use the multiplicative operation. So let me first, since it's a question, let me just color it with some other color. So now 1 is equal to pi of 1, that we know, and this one is minus 1 times, or simply I can write minus 1 square, right?
Yes, sir.
Write it more clearly. So this is minus 1 square. Now, since this is a homomorphism, I can take this square outside, right? This is because phi is a homomorphism. Now what does this implies? So 1 is equal to phi of minus 1 square. That means phi 1 is a second root of unity. Clear? That
Yes.
means phi 1 is either 1 or or minus 1. Simply 1 is phi square minus 1, so phi of 1 can be either 1 or minus 1, right?
Yes, sir.
Now, since phi of 1 is 1 and phi is injective, we are assuming it's an isomorphism. So definitely it's injective. So two things cannot map to the same number, right? So if phi of 1 is mapping to 1, phi of minus 1 cannot be equal to 1, right? Otherwise, these two will map to each other, map to the same number. So phi of 1 is same as phi of minus 1. By injectiveness, 1 has to be minus 1, which is a contradiction. So phi of minus 1 cannot be equal to 1. Clear?
Yes, sir.
This implies phi of minus 1 is 1, minus of 1. So here we are not using the additive part anywhere, right? We have obtained this just by using the multiplicative operation. Now, let's start doing the same thing by taking minus 1 in the beginning. So here we start with 1. Now we will start with minus of 1. So minus of 1 is phi of minus 1, which is phi of eta square, right? This is phi of eta whole square. Clear? Now, since phi is a map from C star to R star and eta belongs to uh, C star, therefore phi of eta must square must be a positive number. Clear? So we are taking square of a non-zero real number. So square is always a positive number inside R star, right?
Yes, sir.
So phi, so that's what I mean to say. So I belongs to C star. Therefore, phi of I, uh, just a second, let me just write it more clearly. So we start with phi, which is a map from C star to R star, and eta is inside C star. So therefore, phi of eta should be inside R star, which is a non-zero number. And if you are taking a square of a non-zero number, it should be a positive number, right? Positive real number. But say this is equation first and this is second. But from second, phi of eta square is -1, which is not a positive number. So this is a contradiction. This is contradiction that there exists a map from homomorphism map from C star to R star. So here, in fact, we are not using the surjectivity. So this implies there is no injective homomorphism from C star to R star, and which implies C star under multiplication is not isomorphic to R star under multiplication. Okay. Here also I should not write just C star and R star. They are supposed to be groups. So is it clear?
Yes, sir.
So just try to use the basic things because that's all we are given here. Just the properties of homomorphism. Now the third part is Z with addition and H is a subgroup of Q under addition generated by 2 by 3. So are they isomorphic?
Yes, sir.
So this is isomorphic. This is not. And why is it isomorphic?
I can define phi from G to H as phi of n equals n times 2 by 3. And it's both bijective and it's a homomorphism.
Once, can you just repeat it once? So this is Z plus, and you are defining from Z plus to this H, right?
Yes, sir.
which is generated by the element 2 by 3. So what is the map?
Phi of n equals n times 2 by 3.
Okay, so this says n maps to 2 by 3 n, right? For all n belongs to Z. Or simply I can write uh, phi, or is it okay if I just define the image of 1?
Yes, sir, since this is cyclic.
This is cyclic, so everything will be generated, right? Okay, so you are right. This is a homomorphism and also a bijection. So this is a isomorphism, right? So is there any doubt in first three questions?
No, sir.
Okay. So let's go to the fourth one. G is S3, the symmetric group on three letters, and H is a cyclic group of order 6. So are they isomorphic?
No, sir.
Why?
So suppose there's some isomorphism.
So that
Um,
phi is an isomorphism from, so I'm denoting it by Z6, right? Z6 is um, cyclic group of order 6. Cyclic group having, or if it is clear, I won't write anything. It's from Z6 to just S3. Yes. Uh, BA isomorphism. Then, yes, Pratna, you were saying something.
yes, so I map identity to the identity. Then,
Okay.
um,
What about the other elements?
then suppose I map the uh, generator to some element of S3. Then
Ah,
I can show that if I take some powers of it, uh, I won't end up with identity. So I'll end up with a contradiction.
I couldn't get. Can you just repeat your argument once?
So suppose the generator
Uh,
of Z6 maps to some element of S3.
Right.
Now, so when I so there's two cases. One is I could map to a 2 cycle or I could map to a 3 cycle.
Okay.
So either way, the generator, if I take the power, um, so when I map the generator, then after if it's a 2 cycle, then if I map of generator times the generator should go back to identity. But this is a 6 cycle, so this won't happen.
Okay. So in the last lecture, uh, we have seen that if phi is a surjective homomorphism, then image of a generator is a generator.
Yes, sir.
You remember that exercise?
Yes, sir.
So I think it was second problem, second last part in the assignment 2, probably. So we will just use the same exercise. So you are also going in the same direction. So I think you are saying that if you map something to a generator, either it's a 2 cycle or a 3 cycle, but that cannot generate S3, right?
Yes, sir.
Uh, or you have some other line of thought. I think that is what you are saying, right? Right,
Yes,
huh?
sir.
Okay. So, uh, so we have seen in the last lecture, the last session, that a surjective homomorphism maps a generator to a generator. Thus, if phi is an isomorphism, then phi of 1 bar, bar is for the element 1 in Z6, generates S3. This is contradiction to the fact that S3 is not cyclic, right? So if there is a generator, that means it is cyclic, but we know that S3 is not cyclic. Okay. Now, fourth one, fourth is done. Fifth one, this is they are not isomorphic. G is Z, and with addition and H is any infinite subgroup of G.
Um, this is isomorphic.
They are
They're isomorphic.
they are isomorphic. Good. What is isomorphism?
I map n to n times the element.
Right. So if H is an infinite subgroup of G, then H uh, instead of G, let me just write Z because here we know what is G. Z, then H is equal to NZ, right? For some N, for some N belongs to set of natural numbers, right? The map phi N maybe from H to from G to Z to H given by um, A going to N of A is an isomorphism. Okay. Now let's move to the next part. Um, Let S3 be the symmetric group on 3 letters and G and H be two different subgroup of S3 of order 2. Are they isomorphic?
Yes, sir.
So why?
So mapping the 0 to 0 and non-zero element to non-zero element, that would be a
So
bisexual.
can we
And
ask a more general question that are two groups of any two groups of order 2 are isomorphic?
um, Sorry, sir, can you repeat?
So here we are taking two subgroups of order 2 in S3. So my question is, like G and HP, any two groups of order 2, will they be isomorphic?
Yes, sir.
Okay, so we don't even need those sub groups to be sitting inside S3, right? So we will prove a more general thing, and the idea is essentially the same, which you have already pointed out. Let G1 is equal to some identity of E1A and G2B E2B B2 groups of order 2 with respect to the operation say star 1 and star 2 respectively. Then the map phi from G1 to G2 given by E1 mapping to E2 and A mapping to B is a is an isomorphism. Clearly, it's 1 1 on 2, and why it will be homomorphism?
So there's only one non-zero element, and so A is A inverse. So inverse of A is also A.
So we just so it's a rough work. I will erase it. So just keep an eye. Let's A1 and A2 be two elements of uh, G1. So A1 and A2 can be A or identity, right? And we need to show that this is phi of A1 and phi of A2. So if A1 equal to A2, then what we will have? So basically, you also know that the order of A has to be 2, right? So A square is identity and B square is also identity in the second group. So if they are same, then whatever these A1, A2 are, whether they are A or even, they has to be even. And again, since phi of A1 is same as phi of A2, this will also become E2, right? The entire thing will become E2 because we are taking the square of the same element if A1, A2 are same. Clear? So phi, when they are same, clearly this identity holds. I hope this is okay.
Yes, sir.
Now, if A1 is not equal to A2, then whether A1 is equal to A or A2 is equal to A doesn't matter. One of them is A and other one is even. So phi of A1, so this A1, A2 has to be just A because one of them is identity and one of them is A. And we know that even A has to be A even and that is as same as A, right? So whether A1 is A or whether A2 is A1, A2 has to be finally A, right? Clear?
Yes, sir.
Now, since one of them is identity, so either phi of A1 is E2 or phi of E2 is E2. So one of them has to be E2 and the other one has to be B. So this has to be B. So if A1 is not equal to A2, this part is phi of A and this part becomes B, which is again true. That's how we have defined phi. So in this case also, this relation holds and thus it's a homomorphism. Clear?
Yes, sir.
Okay. So one habit you start uh, uh, practicing, that never take anything to be trivial. Even things that looks very trivial to you might have a very tricky algebraic proof. So even if it looks very easy, try to show it using the properties. There should be a mathematical proof to every trivial thing. Okay.
Okay, sir.
So that's it. First question is over. Now we can move to the second one. So you have solved the second one or
Yes,
no?
sir.
Okay, good. So let's discuss it together. So in this, we are supposed to select all true statements. This is related to the subgroups which are normal. The first part is every subgroup of the finite of the additive group Z of integers is normal. Why?
Because it's abelian.
Good. Since it's abelian and every subgroup of an abelian group is normal. So this is true since Z plus is abelian. What about the second one?
This is not true.
Every subgroup of the symmetric group S3 on three letters is normal. Why it is not true?
So I consider the subgroup containing the identity and the two cycle 1, 2.
Okay, so solution is for second, take H to be identity. Just I will write E. E is good. N 1, 2, right?
Yes.
So can you give me can you give me an element G such that this element G inverse is not inside H?
So 2, 3 and 2, 3.
Okay, so then 2, 3, 1, 2, 2, 3 inverse, right? That is 2, 3, 1, 2, 2, 3. What it will be?
1, 3, 2.
So 1 is not here, 1 is here, 1 going to 2, 2 is again going to 3. So 1 will map to 3. 3 is going to 2, 2 is going to 1, and 1 is not here. So it should be 1, 3, right? Or I am doing some mistake. 3 going to 2, 2 going to 1, right? And 2 has to be fixed. 2 going to 3, 3 is not here, and 3 is going to 2. So 2 is fixed, right?
Oh, okay.
This
But
is
but still 1, 3 doesn't belong to.
still 1, 3 doesn't belongs to this. This is not inside H, and uh, this implies H is not normal in S3. Good. So, one bonus fact, which is which will give you motivation to read more about these groups. So, this particular thing is known as conjugation. So, when you are uh, having something like that, G, H, G inverse, this is called conjugation of H with G, right? And in symmetric groups, uh, for any element H, GH, G inverse will have the same cycle type. What I mean by cycle type, here you just have two cycle, right? One, two. You are conjugating it with some element. So again, you will definitely get a two cycle. So that way also you can check your calculation. So 132 is not a two cycle. So it can never be a conjugation element of 1, 2. So here you are conjugating with 2, 3. To take any other element and conjugate this 1, 2, you will again get a two cycle only. And if you have, say, some five cycle and some, say, three cycle, and you are conjugating it with something, say in S9, you are conjugating it with some G and G inverse, again you will get a five cycle and a three cycle. You cannot get anything else. The numbers inside can change, but the cycle type will be same, provided here you have disjoint cycles. Okay, Prerna?
Okay, sir.
So that's a bonus fact. Very interesting property of symmetric groups. Uh, but for the moment, you can just ignore it if it is uh, confusing. Okay. So these groups are actually very nice groups, and that's why a lot of people are interested in these groups. Okay. So what about the next? Phi is a group homomorphism from G to H. Then the kernel is always a normal subgroup of G. I think this is already done in class, right?
Um, I don't remember if I have seen this in video, but uh, I think I can prove this, sir.
So let me just maybe I can just say something. Then the kernel of I is always a group, always a group of G. Okay. So don't remember whether it's there in notes. Then maybe I can just quickly say why it is true. So this is a group homomorphism. This is given. So let n belongs to kernel of phi and G belongs to G. Then phi of uh, G and G inverse. We need to show that this is again inside the kernel. So this is equal to uh, phi of G, phi of N, and phi of G inverse, right? And this phi of G is okay. This phi of N is identity of H, right? And this is phi G whole inverse. This is identity, so we can just leave it as it is. We can just get rid of it. Phi of G is same as phi of G times EH, and then you have this. And these are inverse of each other, so this will again give you identity of H. And from definition of the kernel, anything that is mapped to the identity of the codomain is inside the kernel. So this implies Gn, G inverse is inside kernel of phi. And thus, kernel of phi is a normal subgroup of G. So this is symbol for normal. Clear?
Yes, sir.
So this is not normal. This is normal. Next one. Let G be a group and let H1 and H2 be subgroups of G. If H2 is normal in G, then H1 is also normal in G.
Um, this is not true, sir.
This is not true. Uh, why?
Um, I forgot the counter example, but I think I can.
Okay, so here you just think about the counter example. Okay. If you don't get, then you ask me in the next class.
Okay, sir.
I think some counter example exists for matrices. There are many examples, but one such is for 2 by 2 matrices also. So basically, you need to find a subgroup H such that H1 and H2, such that uh, for all conjugates of H2, they are again inside H2, but uh, uh, H1 doesn't satisfy this. And I think you have already mentioned one such example. Very close to a counter example. But okay, so let me just give you a hint. So uh, in S4 you know, right?
Yes, sir.
Mm, the group, the subgroup A4 is normal. A4 also you know,
Yes, sir.
group of all even permutation. But S4 has uh, just one subgroup which is normal. That is S4 only. That is A4 only. So any subgroup of S4 which is sitting inside A4 cannot be a normal subgroup. Also, A4 is the unique normal. I should not write like that. Uh, maybe like this. Identity not equal to H, which is us sitting inside A4. So any subgroup also for any this H is not uh, normal in S4. Okay. So anything which you find inside A4, for example, the group generated by a 3 cycle inside A4. So 3 cycle is inside A4 and a subgroup, it has order 3. So that subgroup will have only 3 elements. For example, you take 1, 2, 3, the groups generated by it will have 1, 2, 3, 1, 3, 2, and identity. So this is a subgroup sitting inside A4, but it will never be a normal subgroup in S4. And the hint is already there in whatever we have discussed. So let me now formally write it. For example, uh, uh, if H is identity 1, 2, 3 and 1, 3, 2, then H is not normal in S4. Can you quickly tell me why?
Yes, sir. So, uh, then G times the well, so even the product of these the three would be a 3 cycle that doesn't belong to
Now,
A4.
so they are inverse of each other. So their product will be identity. It's a subgroup. So you cannot like contradict the subgroup part. It's a subgroup. We are supposed to take a subgroup which is not normal. So it's a subgroup that is given. Conjugate part will give us counter example.
Oh, so if I take some um I'm sorry, I need to think of this.
So I told you that earlier informally that when we conjugate an element of Sn, again we will get an element of the same type, right?
Yes.
Now, one more bonus fact. For any two element which are of same type, cycle type, you always get a conjugating element. For example, there are two permutations, sigma 1 and sigma 2, which have the same cycle type. Then there will definitely exist G such that G sigma 1 G inverse is sigma 2. And that is when sigma 1 and sigma 2 inside Sn. So this is not true for An. And any two element of An may not be may have same cycle type, but still they may not be conjugate. But for Sn, this is always true. So here you can think of a three cycle different from these two, which is conjugate of one of them, but which is not inside this edge. For example, if you take this uh, some cycle which also has symbol 4, then there will be a problem. So to get that, let me just conjugate 1, 2, 3 by something which also has 4 in it. Will it cause some issue? 4 going to 1, 1 going to 2, right? So now what it will be? This will be 1, 4, 1, 2, 3, 1, 4, right? So here 1 is going to 4, 4 is going to 1, so 1 is fixed, right? 1 is going to 4, 4 is not here, 4 is again going to 1, so 1 is fixed. 2 is going to 3, 3 is not here, so 2 will map to 3. 3 is going to 1, 1 is going to 4, so 3 will go to 4. 4 will go to 1, 1 goes to 2, and that's it. So 4 goes to 2. So this is 3 cycle, which is not definitely not inside H. Clear? So this particular conjugate of 1, 2, 3 is 3 cycle 2, 3, 4, which is not inside H. Okay. So always try to put some theory in counter example. Don't try learn counter examples as it is. You will be able to form counter examples instantly if you remember the theory. Okay,
Okay, sir.
clear? This example is clear, right?
Yes, sir.
So this I should not write it's normal. This is not normal, right? Very strange looking symbol. I will just write in words. H is not normal in SO. And the similar same example works for any N, Sn, right? We can again consider the same example because S4 is contained in Sn. So A4 is also contained in An. So the same thing translates for Sn. No need to take just S4. So there are so many counter examples, in fact. Okay. So that part also we have done. So this exercise part is not there. Now what about the fifth one? G is a group and H1, H2 and G are in this sequence. Now here we are asking a different question. The same sequence was there in the above. If the largest one is normal, then the or we have done a mistake, I think. Okay, fine. So if the larger one is normal, then smaller one is not. And here, if the smaller one is normal, then will it be normal in H2 also?
Yes, sir.
It's it's just a one line statement. So if G H G inverse belongs to H1 for all G and so I'm just writing it here. So if G H G inverse belongs to uh, H1 for all G belongs to G and H belongs to H1, then GH G inverse belongs to H1 for all G belongs to G and H belongs to O. Here this G we can also take from H2. So since H2 is sitting inside G and we have a stronger condition that this holds for all G belongs to G, so it will definitely hold for all G belongs to H2 as well, right? So this is true. Clear?
Yes, sir.
Okay. So if you have any doubt at any stage, feel free to ask.
Okay, sir.
Okay. So let me just uh, take the third question. So you have solved this third part also?
Yes, sir.
Okay, good. This is- So if let GLR be the group of n cross n real matrices and R star denote the multiplicative group of non-zero real numbers. We have the determinant map from GLNR to R star. I hope you remember the determinant map, right? A
Yes.
matrix is just mapped to its matrix determinant. Okay. So is phi a 1-1 map?
No, sir.
No. Why?
So consider the 2 by 2 matrix containing three values, so 1, 1, 1 and 0.
3 by so 2 by 2 matrices. Uh, so let me just give some name. A is you're taking two matrices now. So what is the first one?
A11 is 1
One, one,
and A21 is 0, A22 is 1.
A. No, A21 is 0 and A this matrix. Can you just tell me like this entry first and then this and then this and this? So what is this entry in your matrix?
Sorry, sir, there was a slight disturbance. I couldn't hear what you said in the
Oh,
last
so
few seconds.
can you just repeat your matrix? What is the entry, the first entry, 1 2 entry, 1 1 entry?
The one you have written is what I wanted to tell, sir.
Okay, okay, very nice. What is the second one?
A transpose.
A transpose. This is 1 0 1 1, right? Uh, right. So both of them have let this, and then uh, you are absolutely correct. Determinant of A is equal to determinant of uh, B, which is 1, right? So pi is not surjective. Oh, sorry, injective. Injective or 1 1. In fact, we can say a bit more. So, in fact, determinant of A is equal to 1. Uh, this forms a group that is SL and R, right?
Yes, sir.
So the entire map group is mapped to determinant 1. There are so many matrices. Okay. So that's what you have taken. So both elements are from SLN2, right? SL2R, sorry. Both elements are from SL2R. Okay. Is it on to?
Yes, sir.
Why?
So for any R, I have R times identity mapping to it. So
So will it give you uh, determinant R?
yes, sir.
So you want to say RIN is R, right?
Yes, sir.
But in multiplication, determinant of RIN is Rn times determinant of In, right? Determinant of some lambda times A is lambda raised to n into determinant of A, where n is the order of A, right?
Oh, yes, sir. I forgot
This is
about.
true only when this R is a nth root, but that may not be true for all real numbers, right?
Yes, sir. I'm sorry, forgot about that.
So there is also one simple matrix which you can consider. So let some R belongs to R, then the matrix. So you have everything 1 except one entry, which is R. And then this is on the diagonals, and all non-diagonal entries are 0. Very bad in drawing. So this matrix has determinant R, right?
Yes, sir.
Because it's a diagonal matrix. So determinant of a diagonal matrix is just the product of entries, which is R, right?
Yes, sir.
So this is 1 1. Oh, sorry, this is on 2. So let n greater than equal to 2. There exists a matrix A in the kernel of phi such that A is not the identity matrix.
Yes, sir. The example for the first one
The
itself.
first example. So kernel of phi uh, means all matrices which are mapping to 1. So I can simply write C solution or Simply, I can point out to these examples. Good. If A and B are two matrices in the kernel of phi, then A plus B is also in the kernel of phi.
This is not true. Again, we can use the example, first
Very
example.
nice. So you have constructed one example which works for all three.
Yes.
Good. So again, this is not true. Same example will work. So maybe we can move to the next problem. We will select all true statements. A group of order 84 cannot have an element of order 8.
This is true, sir.
This is true. Why?
Lagrange's theorem.
So do you remember in lecture notes whether it something like that is proof that an order of an element divides the order of the group?
Mm, Yes, sir.
Is it there, right?
Yes, sir.
Okay. So first, uh, first one is first two elements. Just the first part is a consequence of that. So they should have given some numbering to it. Okay. So first one is uh, this is a general statement, so I'm writing it like that. Uh, Order of an element divides the order of the group. Okay. This implies first one is not true. Since 8 is not going to divide 84. What about the second one? A group of order 84 cannot have an element of order 12.
This is false. 12 divides 84.
So
So,
again, this is false because so this is true. Oh, first is true, right? This is not false. First is true, and why second is false? It is saying cannot have means in every situation it is saying we cannot have an element of order 12. But there are groups for which uh, groups of order 84 for which uh, there is an element of order 12. It's not guaranteed that we will have an element of order 12, but there are some groups for which this is true. So can you just give me a group of order 84 in which there exists an element of order 12?
Z84.
Huh?
Z84.
Z84. Very nice. So the group Z84 has an element of order. What is the element? Or what are the elements?
I don't know w- what to call the notation, but 12, um, 12 bar. So that generates whatever group the element 12 bar generates that has um,
But 12 bar has order 7.
I'm sorry, the opposite.
Huh?
8 bar. So the group generated by 8 bar, um,
So the element 8 bar, you want to say?
yes,
But 8 bar will not have. So the element,
sorry, 7 bar.
very nice. So 7 bar has order 12. Just divide 24 by 12. Now, a cyclic group of order 345 have exactly one group, subgroup of order 23.
This is true, sir.
This is true. Why? Simply, we have seen that for any divisor of Zn, there is a unique subgroup, right? So since 23 divides uh, 345, right? It's dividing, right? 15 times it divides. And what about the last one?
No.
It does not have a subgroup of order 26 because 26 does not divide 345. So all subgroups of cyclic subgroups are corresponding to divisors of n. Subgroups of Zn are precisely uh, given by divisors of n. And there is a unique uh, subgroup for each divisor. So since 26 does not divide 345, so there won't be any subgroup. Okay.
Excuse me, sir.
You have
Um,
any doubt, Prerna?
yes, sir. Yes, sir.
Huh?
So, for the example of Zn, it can be shown that it has a unique subgroup of order 26. But how to prove that generally?
So for Zn, there is a unique subgroup for each divisor. For
Okay.
each divisor, there is a unique subgroup of. Uh, so let me just write it. For the cyclic group, Zn, the subgroups corresponds to divisors of n. Or instead of the, I should write all. Subgroups corresponds to a divisor of n. And also, if D divides n, then there is just a there are just a unique subgroup of order D, uh, generated by which element? N by D bar. And in fact, these are the only subgroups. These are the only subgroups of Zn. So if there is a group of subgroup of order 26, it has to be generated by n by d bar. But there is nothing n by d bar, na? And n is not divisible by d in this case. So there won't be a subgroup.
Yes, sir. So I wanted to know
So you wanted
how
to
to
know the
prove.
proof.
Yes, sir.
So uh, I can just give you some hints and you build upon those hints. So as your group is cyclic, the all subgroups should also be cyclic, right?
Yes, sir.
Subgroups of a cyclic group is cyclic. Now, if there is a subgroup of order 26, that means there is an element of order 26 because it's a cyclic subgroup.
Mm,
Clear?
yes, sir.
So, say let A belongs to Zn. So if D is not dividing N, what is the situation? So let A belongs to Zn such that order of A is D, right? In this case, N is 345 of D and D is 26. So you use the Euclidean algorithm. N is dk times R for some k and R belongs to N. And uh, this R uh, is non-zero. Or I will say 1 less than equal to R less than equal to N. So this R is strictly non-zero. Less than equal to D minus 1. Because if it R is 0, then D divides N. Now you take A raised to N. This is A raised to order of G, right? Which is always equal to identity. Any element raised to order of G is identity. Clear?
Yes, sir.
Why? Because order of an element always divides the order of the group. So this order of G is that, and then this is A raised to dk plus R, which is A dk AR. And this part is trivial because A raised to D is identity, but this is not equal to identity, right? So this whole is A raised to R, which is not equal to identity, and hence it's a contradiction. In one part, you are getting identity. In another part, you are not. Clear?
Yes. Yes, sir.
So the contradiction is basically coming from the fact that order of A is D. Even if you know the answer that, if you know that statement that order of an element divides the order of group, you are done at this step only. Because here you are getting an element whose order is D and D is not dividing the order of group. So this is a contradiction itself.
Yes, sir.
So no need to do all these things if you remember the statement that order of an element divides the order of group. Okay. And
Sir,
then, huh.
so if they are ordered, so if they ordered, so I wanted to prove the third statement to show that there's exactly one subgroup of order 23. So in if we take the general statement,
Mhm.
when the order divides the order of the group, then how to show that there's only one subgroup of order 23?
Uh, okay. So what are the elements whose order, say for D? D is a divisor of N, right? Now, what are the elements which will have same order as, uh, which will have order D? Given any N and any divisor of N, what are the elements which will have order D? So
The
do you
generator.
understand the question? So let D divides N. Uh, so what are the elements in Zn which has uh, what are the elements which have order D? Definitely one such element is D by N bar. Oh, I have done in the opposite ways. One element is N by D bar. What are the other elements which will have order D? So you just check uh, any element of the form A D by N where uh, how to write this? A and N has GCD1. That is at least we require. Again, I am doing the same mistake. N is bigger, so it should come again. Okay. Uh, N A by D. For example, you consider Z6. In Z6, what are the element of order 2, 3 bar, right? And here it will be order 3 element we should consider. So what are the elements of order 3 here? 2 bar and 4 bar, right? 4 plus 4, 8, which is equal to 2 bar. And again, plus 4 is 12, which is identity. So these are the elements of order 3, right? So this is 2 bar and 2 times 2 bar. So 2 is co-prime with 3. So all those elements of the form Na bar by D, where A and D, I think, D should be co-prime. All these elements will have order D. You agree with me?
Yes, sir.
Uh, You just give it a thought, it will be clear. See, if you are multiplying something which has a common factor with D, then you know no need to add this D many times. For example, if you are multiplying NR by D, where R and D have some common factor, say K, uh, then you can do this instead of adding uh, these many times. You can simply add this D by K times. So this element will have order D by K instead of having D. You just give it some thought, it will be clear. So these are the all elements of order D inside Zn. Now you look at the group generated by uh, N by D bar. All such elements are inside this. And in fact, the group generated by any such element will be same. So this is same for all A with A comma D is equal to 1. So whatever generate element of order D you pick, you are anyway going to get the same subgroup. That's why the subgroup is unique. Is it clear, Prerna?
Um,
Or you
yes.
want me to explain this with the one example?
No, sir. I think maybe I'll take this as an exercise and.
Okay, you just work with Zn. So Z10. So here elements of order 5 you consider. Order 5 elements are 2 bar. Now you multiply 2 bar with anything which is co-prime to 5. So 2 you can multiply 2 is 4, 4 bar, 6 bar, 8 bar. These are the 4 elements of order 5. Now you take any of these elements, you will be getting the group generated by 2 bar inside Z10. 4 plus 4 is 8. So this will come. And then again, if you add, maybe some mistake I'm doing. Just a minute. 4 plus 4 is 8. Right. And if you add again 4, it is 12, which is 2 bar. If you again add 4, then it is 6. So all these elements will be there. And again, if you add 4, this will be identity. So there will be 5 elements inside this subgroup. Similarly, if you start with 6, 6 plus 6 is 12. So this 2 will come, 2 plus, then again you add 6, 8 will come. Again, you have add 6, 8 plus 6 is 14. So this 4 will also come. Similarly, you start with 8, you will get the same subgroup. So any element of order D you start with, you will end up with the same subgroup. That's why there is a unique subgroup of order D. Okay.
Yes, sir.
So you take it as an exercise. If you don't get it, then maybe we can discuss more in the next session. Okay.
Okay, sir.
So let me just erase it because this is very vaguely written. But I think you got the idea, right?
Yes, sir.
Okay, great. And maybe we can move to the next question of the practice assignment. Okay. This is also the last question in this practice assignment. If time permits, then we will be discussing some more problems apart from the practice assignment. Okay, so fifth question is, let Q star with a group of non-zero rational numbers under multiplication, and then define an equivalence relation on Q star by declaring A related to B, AB greater than 0. How many equivalence classes are there for this equivalence relation? Yes,
Mm. There are
there are
two equivalence classes.
two equivalence classes. What are those?
To the positive rational numbers and
Positive
the.
rationals and negative rationals. There are two equivalence classes. So can you just tell me why?
Yes. So due to the property of real numbers, um,
Property of
um,
real numbers.
property of rational numbers, if A A is positive, um, and AB is positive, then this implies that B is also positive. Similarly, if A is negative, and if A times B is positive, then this implies that B is also negative. So um, we can see that there are two equivalence classes where one consists of the positive rationals and one of the negative rationals.
Uh, Having two equivalence classes means if I take any two elements in this class, they should be related. And similarly, if I take any two elements in this class, they should also be related.
Yes, sir. So positive rational times positive rational is positive.
No, no, no. Positive rational times positive rational doesn't mean that all positive rationals are related. So what we are supposed to show, uh, if A and B are two positive relation uh, are two positive rationals, then look at the definition of being related. Okay, okay. I was just misinterpreting this relation. You are right. Product of two positive rationals is again positive rationals, so they are related. And but then this doesn't form a equivalence class, right? A is related to B is AB is greater than 0. So why two negative rationals are related? Their product is again greater than 0, right? So if two are positive or negative, are both positive rationals or both negative rationals, and we can simply write instead of to show proof, then AB is greater than 0. So they are in one orbit and they are also in one orbit. We also need to show that if A is positive and B is negative, then they cannot be related, right? Why is it so? Because their product is less than 0, right? This implies A is not related to B. Clear, Prerna? This is what
Yes,
you were saying?
yes, sir.
Good. So we are done with the practice assignment problems. So still we have time. So maybe we can discuss some more problems apart from the practice assignment. Let me write some of them for you. Start, let us start with a easy one. Uh, the number is also there. So just forgot this number 2. I have just taken it from somewhere. So this number is also coming. Can you prove this? It's an easy one, I guess.
Yes, sir.
How? G is an abelian group. Then for all AB belongs to G, we are supposed to show that AB raised to n is AN raised to AN times BN. So you want to start of your own, or
So,
maybe if you have some idea, then you tell and then I will proceed based upon your inputs.
well, so AB times AB power n is AB times AB n times, right? So, and since G is abelian, um, I can um, I can change the order. Then I can get A power n times B power n. That was my idea.
Intuitively, you are correct, but there should be some more clarity on this. So can we use induction, mathematical induction for it?
Okay, sir.
You know induction, right?
Yes, sir.
So uh, we can prove it by using mathematical induction. Whatever you are saying is okay, but there is uh, some unclarity there, right? Uh, Intuitively, you are correct that we can swap the elements and then we will get AN one side and BN one side. That's what we are going to do, but in a more formal way. We can prove it by using induction. So at n equal to 1, of course, AB raised to 1 is AB. So we are done. Now we can assume that let it be true for n equal to k. That is ABK is AK BK. And we need to show it then for n equal to k plus 1. So then this will be AB raised to k plus 1. And this is same as ABK times AB. But ABK is AKBK. And you have AB. Since we are in abelian group, we can swap these numbers, these elements, and we will get A raised to k plus 1 and B raised to k plus 1. Okay. This implies ABN is equal to ANBN for all n. Now, this is for posit principle of mathematical induction is for uh, positive integers, right? Here it is for it is demanding for all integers, means n can be negative also. So the first case was when n is positive, right? Then this induction is fine for all n greater than 0. That's what we have done till now. Now, for n equal to 0, definitely we have AB raised to 0 is identity, A0 is B0 is identity. So nothing to check there. And uh, if n is less than 0, then we cannot use mathematical induction, right? Mathematical induction is for positive integers. But uh, still we can say something. Then let m is equal to minus of m. This is greater than 0. Then this will implies AB of n, which is AB of, so okay, I can write it like that, minus of n, right? This will be AB inverse raised to minus of n. AB inverse is B inverse A inverse raised to minus n is m, which is greater than 0, right? So for this part, we can use from, oh, sorry, not for this part, the coming part. So this is two elements which are raised to minus n. Minus n is positive. So we can use the first part where we have established this relation when the power is positive. This will be B minus 1 raised to minus of n and A minus 1 raised to minus of n. For this part, we have used part 1, right? Now B raised to minus 1 times minus n is just B raised to n, and A raised to n. But since it is abelian, so this will be an dn. Okay. Anyway, this part we cannot do by intuition that you were saying, right? Because the power is negative there. So for this
Yes.
part, anyway, we need to take the inverse to make the power first positive, and then we know the answer for positive one, so we can use it. I hope it's clear.
Yes, sir, it is.
Okay. So we can discuss some more problems. Let me just write, see some good problem to give you. If G is a group such that AB whole square is A square B square for all AB in G, then we need to show that G is abelian. Again, you can forget this number. This is coming due to some reason. Yeah, I can write question 2 and so got the problem, right?
Mm, yes, sir.
So this thing, so the converse of this statement, but a very weak converse, or in other way, very strong in the converse direction. So if abelian, we know that ABN is AN BN for all AB and for all integer n. But what it is saying that if in the converse direction, the relation is true for just n equal to 2, then G must be abelian. So in other way, this question can be reformulated as if G is a group such that, so let me uh, just write it in some other way. So, or if A dot B square is A square B square for all AB belongs to G, uh, then ABN is equal to AN BN for all AB belongs to G and N belongs to N. Why? Because instead of N, I should write it as a corollary. Because once you prove that the group is abelian, again you can use the first part and show that for all powers N, this relation holds. So as a corollary, this says that if you have this relation for the n equal to 2, then you will have it for any n, which is a very nice statement, right? Now, so you just need to show that G is abelian. You will get this statement as a bonus. Can you tell me the proof? The proof is very easy.
I just have the idea.
Huh?
So suppose that there are two elements A and B such that AB is not equal to BA.
AB is not equal to BA.
Then I have AB square to be A square B square and uh, BA whole square to be B square A square.
Mhm. The easier thing will be to do it directly without contradiction. So since A dot B square is A square B square, you just open
Yes,
it.
sir. I think I got it.
Okay. Tell me.
So AB square would be AB AB.
Uh,
Then A square B square would be AA BB.
right.
So now A inverse times AB AB equals A inverse times AA
Simply we
BB.
can cancel now. I think you know this left cancellation, right cancellation. Na? A will be
Hmm.
cancelled by this A and this B will be cancelled by this B, right?
Yes, sir.
I'm just multiplying by A inverse both sides from the left and multiplying from by B inverse from the right. So these two B will be cancelled out, right?
Yes, sir.
Clear na?
Yes, sir.
This side will give you BA and this side will give you AB. BA is equal to AB for all AB belongs to G, and this implies G is abelian. Okay. Still there is some time, so we can discuss probably one more question. Uh, Very good question, but it will take some time. So maybe that question we will discuss in the next session, but uh, a smaller question we can discuss. Okay, so this question is so we have shown that uh, if AB whole square is equal to A square B square, then the group is abelian. Now you know that S3 is not abelian, right?
Yes, sir.
So uh, in a S3 there should be two elements for which the identity is not true.
Yes, sir.
So can you just find two elements in S3 for which XY whole square is not same as X square Y square? So it's a very natural question to ask, right? Because S3 is not uh, abelian.
Yes, sir.
Try to find. Now you know everything about S3. Just find two examples. two elements. A hint is one such pair is when you take uh, X to be a order 2 element and Y to be an order 3 element. Even if you take both to be order 2 distinct elements, then also I think this should be. Yes, Rena, you got something?
I'm still thinking of it, sir. Just trying to calculate and ensure that it's correct.
Del, you can also speak. Uh, so, what are the two elements that you are thinking of? Maybe we can verify it together.
1, 2, and 1, 2, 3.
1,
But
2, and 1, 2, 3. So
I'm
let
still not sure.
X is 1, 2, Y is 1, 2, 3. Uh, then what is X square? X square is identity. What is Y square? Y square is 1, 3, 2. What is X times Y? This is just 1, 2, 1, 2, 3. So 1 going to 2, 2 is again going to 1. This is fixed. 2 going to 3, 3 going to 1, 1 going to 2, 2, 3. So this implies X, Y whole square is equal to 2, 3 whole square, which is identity. And X square, Y square is identity times 132, which is 132. So clearly they both are not same,
Yes, sir.
right? So good. Can come up with the right example. So are there any doubts?
No, sir.
So if no, then maybe we can stop the meeting. From the next session, we can also discuss the assignment problems because I think assignment 1 has deadline to be 6th August, right?
Yes, sir.
So by the next session, the deadline would be over. So we would be free to discuss assignment 1. So we can start discussing assignment 1 onward from the next session. Okay. And
Okay,
you do submit your assignments if you want to get the certificate. I think you might have gone through the percentage distribution between these assignments and the final exam, right?
Yes, sir.
So
I have
there are
already submitted the assignments.
there is weightage for this assignment also. Okay. Okay. So maybe I can stop sharing and okay, I will end the session. If you have any query or any doubt, then you can ask. Otherwise, I will end the session here.
There are no doubts, sir.
Okay. Thank you. So, see you on next Tuesday. Bye.
Thank you, sir.
Okay.